Are you guys picking on Jamie? See a lot of talk about Jamie. It's fine if you are. I just want to know.
He left a good luck message on the exam and left my name on it, and somebody was asking if he was playing favorites, and I was saying no. It's probably more of like he realizes that I need all the help I can get, and I was saying that if Jamie gives me a high grade on the exam, then I'd offer to carry him in a video game. So I guess in a way, yes.
Oh, I thought for sure he was asking about the runtime to calculate the number of Jamie's friends. Jamie said according to OMS Central, it's going to be O of 1.
Let me tell you, Jamie is frustrating to play video games. It's not frustrating. I jab at him all the time when we play video games. It's pretty funny. We actually end up playing games quite a bit. But like when you can't reach either of us, it's probably because we're playing video games.
All right. Does he carry or do you carry? Asking for a friend.
Also, is this like you guys play a particular game or you guys play a certain role? Because I feel like I could discern a lot of your personality characteristics if it's like, I don't know, when he plays tank or support or something like that in a game like that.
Joves told me that he likes to play support characters, and so I try to test that theory as much as I can with every game we play.
Wait, so
I
Jamie
spend more time. I spend more time resurrecting Jamie than I do anything else when we play. Picking him up, making sure he stays alive.
As somebody that plays supports are the most valuable characters, and I will not hear a counter argument against that because there is no counter argument against that.
All right, I'm gonna start because other people were probably like, man, what a bunch of nerds. Right, 8.16. I do not like the wording of this problem. There's a lot of issues with this wording because I think it's trying to get you to make a few leaps. And so it gives you a few misdirections. So first of all, it's not an NP complete problem as presented. It's actually an NP hard problem. And then what it wants to say is, well, if you can solve this in polynomial time, then so is 3-sat. And so if you were to read this, like I did when I first tried to solve the problem, it's like, oh, it wants me to use 3-sat to do the reduction. And it doesn't. 3-sat would be a very difficult reduction from this. What it ends up meaning is that the statement, if this is solvable in polynomial time, this being an NP hard problem, then an NP complete version of this problem is also solvable in polynomial time. And if an NP complete version of this problem is solvable in polynomial time, then so is 3-sat. So that's what that sentence sort of means. But one, you shouldn't try to solve this as you should try to solve this as an NP complete problem. And two, you should not try to use 3-sat. So the way I'm going to solve the problem is that because this is not a standard NP complete reduction, I'm going to change it so that I would add a number k such that we need greater than equal k ingredients with penalty less than or equal to p. That way we can go through like the full reduction of what we do in this class. Let's see. Why does OS paste to the side? Okay, so I am going to be using what did it say? Oh, independent set. Yeah, so I'm going to use independent set, and then this is my NP proof. So given the input, we look for a solution. And so let's see. We can confirm that the size of S is greater than or equal to K. K is the thing that I put in here just so that I can make it into an NP complete problem, and that the penalty between each pair of ingredients of S adds up to less than or equal to P penalties. It takes all n to count S, and O of n squared to compare O pairs in S. So the runtime is O of n squared. Okay. Because if we don't do it this way, if we don't add the k thing, the output is the maximum number. It becomes a optimization problem, which is actually like pretty difficult for us to kind of work with. So I wanted to make this an NP complete problem. So that's my NP proof. Just basically check that I have k ingredients and that I have why is this? I have not gone over my penalty limit. Okay. And so because we're going to do this independent set, and this is not something that's like would be really easy for you to kind of like see. It does take a few like leaps in order to get this from one to the other. Right. So we start with an independent set with input G and K, and we create a matrix such that any two vertices with an edge to each other has a penalty set to 1. Any two vertices with no edges to each other has a penalty set to 0. So then we pass in the matrix k equals k, so that we want an independent set or the number of ingredients to be some k, and we set the penalty to 0 with the experimental dish black box. This takes O of n squared to set the values of the matrix and based on G. And then on the output, we return no if there's no solution. And then given the solution to experimental dish, we return the set of ingredients, which are vertices, back as an independent set. This takes no transformation and so on. So the idea is that if I have a graph, I want to avoid edges completely. I want, let's say I want, that's actually not going to have an independent set, is it? Right? I want to return two of these vertices such that they don't share an edge together because it's an independent set. So if I set this penalty equal to 1 and this penalty equal to 1, then my ingredient thing isn't going to select both of these vertices, because otherwise I incur a penalty of 1, which is greater than 0. I'm also not going to select both of these vertices, because again, that would pay a penalty of 1, which isn't allowed. What I would end up doing instead is I would select, this one in this one where there's no penalty between them, and therefore I don't, they count as my independent set on the graph part, and that's how you kind of set this up. So these two vertices with no edges to each other has a penalty of 0. So you pick this one, pick this one. Okay. Hopefully that.
If instead we try to do this with a clique, and we reverse the logic that you had, if there is no edges, then we set to 0, and if we don't have an edge, we set to 1, and the other way around, we set to 0. And if we solve it with a clique, is it equivalent to an independent set?
So if they have an edge to each other, we would set that to 0. Yeah. And if they don't have an edge to each other, we would set a 1.
Yep.
So that it is the inverse, and we say pick I want to say yes, but I have to think more carefully about it. Would I get into a situation? I think that could work. Yeah.
All
right. 2 questions. The first one, why do you need to prove it is NP? I think this problem does not require us to prove it is NP, right?
Yeah, I modified the problem so it fits this class better.
Actually, you don't need to, and you can just work on the optimization version, because you know you have a powerful algorithm to solve this hard problem. Then you can use it to solve the.
But I didn't want to present this problem in such a way that like deviates from what this class does. So I set it up to be a complete problem.
I see. Thank you.
All right, let me paste my correctness. So I illustrated it, and then this is just explaining it in words. So we've created a matrix such that any two vertices that have an edge between them is set to 1. Any two vertices without an edge is set to 0. We then force the experimental dish to find a set of ingredients with no penalty. So no edges between vertices and at least k ingredients. This is equivalent to looking for k vertices that share no edges. So if independent set has a solution, create an input for experimental dish. If independent set does not have a solution, then because we created input that would be not have enough ingredients that don't have a penalty between them, experimental dish also cannot find k ingredients with no penalty. So yep, that's just basically how we set it up. Any questions about this one?
So given the problem input statement have a penalty that is less than equal to, at most, can we rephrase that P as a budget and use vertex cover?
I think the vertex cover could, I mean, all of these are NP complete problems, right? So they can all work. It just, when you go into the exam and you're gonna have this issue where it's like you look at the problem, you go, can I do this with SAT? And the answer is yes. Can I do this with the vertex cover? And the answer is yes. Can I do this with knapsack? And the answer is yes. Because all NP complete problems, they reduce each other. So there's no limit to which NP complete problem you can use. But there are certainly going to be ones easier than the others, and one that is much less prone to error. So your job is to figure out what matches best and how to think about and approach that problem to make your life easier. And two, we get a lot of students that will be like, the problem is clearly to use a click, right? Like when you look at the Spider-Verse, it's clearly to use a click. And then you try to do an independent set. And while that is doable, most of that is to take the independent set problem, invert it, turn it into a click problem, and then do Spider-Verse with it. That's like the most general way to do it that way. And then students will be like, well, I chose to do something different, and that's okay. But you're likely not going to do it well. Some reductions are very difficult and not encouraged at all. So I would say that yes, you could probably do this with vertex cover. I wouldn't bother learning it. Learning it means you have put into your mindset in such a way that like you would try to do this problem with a vertex cover when it's certainly easier with independent set. Does that make sense? I don't want to say like you can't do it, but I do also want to discourage you trying to do it.
Yeah. So I can see it's much easier to do it from independent sets when we can do the set the R equal to 1 when there's a edge, and then R equal to 0 if there's no edge.
Yeah.
I guess the question is that during exam 3, how can we think the right direction and then pick the right NP completeness problem to reduce from?
Well, if you get a problem that says it's a click plus these other things, you should start with a click, right? Like Spider-Verse is a click plus legs. So you should certainly do a click. You shouldn't try to do independent set. And I've seen students do it. I have never seen a student do it correctly. That's just the way it turns out. I would say that a student that sees the Spider-Verse problem, sees that it needs to start with a click, decide, you know what, I want to do vertex cover, either they're exceedingly brilliant and challenge themselves and is good at doing it, or two, they haven't studied well enough to know which problems they should have started with. It tends to be one or the other. There's no like middle student that's like, I'm going to do it this way just because I think it might be fun. And so to answer your question, how do you use the right one? I think you have to pick up on clues, and you get that through experience, trying the different practice problems, trying to see different practice solutions. And that the entire earlier section on the graph transformations kind of gives you an idea of like what kind of things you can do to do the manipulations. I don't think there's like a hard rule to be like always use click on this type of problem, always use independent set on this type of problem. Other than the fact that if the problem says it's a click plus something else, you should probably use a click.
Thank you.
Any other questions on experimental dish?
Yeah, I had a quick question. So the problem says to, sorry, could you go up for a second to the problem statement? It says, show that if experimental cuisine is solvable in polynomial time, then so is 3-sat. So would you just say like, since 3-sat is reducible to independent set, and we proved that independent set is reducible to experimental cuisine, then
honestly, I didn't even bother answering the question. But if you wanted to, all you have to say is that this proved that this problem is NP complete, and if this NP complete problem is can be solved in polynomial time, then all NP complete problems is solvable in polynomial time, and 3-sat is an NP complete problem, and therefore it is also solvable in polynomial time. But again, I think it's just like a really weird way to word this problem, and I just completely ignored it.
Okay. And then I was wondering if you think this is a viable solution I put in the chat for reducing directly from 3-sat is sort of like mimicking the reduction from 3-sat to independent set, where all the literals are mapped to ingredients, and then opposite literals get a max discord of 1, and then all the literals in the same clause get a max discord of 1 as well.
So again, this goes back to what I'm saying. Like, yes, if you forcefully wanted to do this from 3-sat, you can. I would not recommend it, and I would. And I guess this one's worded weird in that it kind of gives you the bad impression that you should do from 3-sat. We would not do that on the exam. We would not be like, this is clearly independent set reduction. Why don't you try 3-sat? Like that would just be cruel and not okay. And so I wouldn't try to do this with 3-sat.
Okay.
Well, they probably could. Like I mean, I wonder if like the original writer of this problem actually did do it from 3-sat. Like, to me, it's clearly more difficult. So I don't know like why you would do it that way. Yeah. Although, yeah, whatever you're doing from 3-sat to independent set, you would do something similar, because this is basically, when you set it to zeros and ones, basically a independent set problem.
Yeah, exactly.
Yeah. Okay. Next problem is worst case scenario for ONP. This is 2.17. Right. So this is another one of those problems that's like not really in the format of what you would expect on the exam. And I don't think you have to like be able to prove this kind of thing, but just kind of be able to understand what I'm about to show you. So the way the question is that show that any problem, is that pi? What is that symbol? I, what does it? Anybody
It's
know what
capital
that symbol is?
pi. Capital pi.
Okay.
Yeah, when I copy
call
it
it-
from the textbook, it's definitely pi.
All right, I'm going to call it pi. So that for any problem pi in NP, there's an algorithm which solves pi in O of 2 to the p of n, where n is the size of the input instance, and p to the n is a polynomial which may depend on pi. Okay. What this problem is trying to establish. Oh, sorry. I'm gonna cough a second. My voice just went real harsh. All right, I don't know. I don't know if my voice is going to be able to keep up. Let's hope it stays. Okay. What this problem is trying to do is it's trying to set an upper bound for all NP hard problems. The idea is that, like I said earlier, that while we mostly consider in this class within scope that a problem is either polynomial or it's either P or NP, there's actually other class spaces around. Did someone link the YouTube video on the complexity zoo of problems?
Yes.
Great.
It was on
Great
one
video.
of the pin posts.
Yeah. So great video. You should watch it. One of my favorites. So once you understand that beyond NP, there's more difficult problems. This question is trying to establish an upper limit of how hard can the class of NP problems be. Okay. So show that for problem pi, there's an algorithm that solves it in 2 to the p of it. Okay. So I'm going to paste my solution here, and then I'm going to talk through it. Know that you probably don't really have to fully understand the details of this. This is just sort of how we get there. Okay. So we know what pi is NP because we already talked. It's established. Then there must exist some algorithm that can verify the solution in polynomial time because that's what the definition of NP is. So we're going to call this special algorithm V. Okay. Our verifier of our algorithm, verifier. And since the algorithm is bound to polynomial time, right, because we know this, that's how NP verify has to be, then the solution that it must verify is also bound to at least that many bits, right? And this is sort of the first jump of intuition we have to take. Consider if you are trying to verify a solution of size 100, and I say that I have an algorithm of that runs in runtime of 2, right? That's impossible. Just reading the solution to verify it takes a runtime of 100. So therefore, it's impossible for me to say that I have a verifier that runs in runtime of 2. And this is just arbitrary numbers. So what I'm saying is that the number of bits that represents our solution must be within the limits of our polynomial runtime. Okay, and so that's in order to perform the verification of solution in V of n, then at the very least V of n bits need to be read. If the solution of bits to be read is greater than that, then V of n cannot be enough to verify the solution. Okay, so then since the solution is the most V of n bits, we can solve it. We can solve pi by trying every single possible solution, right? So we are going to forcefully run binary search on every single possible solution. So if you consider that V to the n bits can represent a number this big, which is 2 to the Vn, right? That's just how bit works. Then it would give us, let's represent that as k. It would give us 2 to the k possible solutions to verify. Okay, and all I did was verify V to the V of n with k to make it a little bit easier to read. Okay. And since we have a v of n a verifier, and we need to verify 2 to the vn possible solutions, our runtime to find the solution is v of n times 2 to vn. That is, we take our verifier and run it against every possible solution to see if there is a solution. The next step is that since we know that v of n is polynomial, it must be smaller than exponential. And if it's smaller than exponential, we can derive this equation right here where v of n is less than or equal to 2 to the n. 2 to the n is exponential. We know that our verifier is less than exponential because it's polynomial. If we substitute v of n for 2 to n, because we know that's our upper bound, it's an exponential number, so it's our upper bound. So then we get 2 to the vn times vn is equal to this equation here. Okay. So I've established that this is less than this. So therefore, when I want to multiply these two numbers, I set it up as 2 to the n. I replace v to the n with 2 to the n, and I know that this is my this is the number of possible solutions I have to verify, and this is how long it takes to run my verifier. And so since n plus v to the n is still polynomial, so this 2n to the n is polynomial, we can replace this with p to the n, which is what we were stating before, which is that we want to have p to the n is a polynomial that's dependent on the pi. We know that this is polynomial, so p to the n is dependent on pi. So this gives us a final worst case runtime of 2 to the n plus v to the vn equals 2 to the pn. And that's how we arrive at this equation. And so our overall runtime is O of 2 raised to pn. And since we know p and n is a polynomial, that actually gives us this little detail, is that we have just proven that if a problem is considered to be NP complete, it is in worst a exponential in runtime. This doesn't. There's a different method of saying that NP hard problems is also within exponential in runtime, but this is just working on NP complete problems. And I think this is the most important detail that you should hopefully have gathered, is that NP complete is exponential at worst. And we're trying to see, like, even though we know worst case these are exponential, can this be polynomial instead of exponential is what we're trying to figure out. We do have a worst case upper bound for it though. Okay. Any questions on this?
I don't have question, but I think the bit thing is a little bit confusing. I have a more straightforward way to prove it. Just reduce this problem pi to set or 3 set. Because in set or 3 set, you know the number of possible solutions is 2 to the n, or 2 to the pn, which is the size of the problem.
Yeah, I mean, there's certainly probably better ways than what I've heard. So if you wanted to present this, go to the office hour and says, hey, this is my my proof of 8.17. I'm sure other students would appreciate it, and that's great. That's fine. Maybe I'll steal it and use that the next time I have to present this problem. All right, 8.19, 8.2, and 8.22. We are almost done. 8.19 is kite. Kite should be very similar to spider. It's a little bit different. Okay, so the key to kite that's different than spider and some other problems that, and this is what students might be confused about. I'll explain. A kite is a graph on an even number of vertices, say 2n, in which n of the vertices form a clique, and the remaining n vertices are connected in a tail. that consists of a path joined to one of the vertices of the clique. Given a graph and a goal G, the kite problem asks for the subgraph, which is a kite and which contains 2G nodes. Prove that kite is NP complete. The key word here that you end up getting is subgraph. Kite returns a subgraph. So what that means is that the kite that you get, the solution you get, is the vertices plus the edges among them that creates a kite. You don't need to do an induced subgraph on this because the induced subgraph might not be a graph, whereas the subgraph itself is. And so what that means is that like if I had a graph like this, and then let's say 1, 2. Okay, that is a kite. If I had an edge right there, right, that would not be a kite. And if I was to only hand you back the vertices of these right here, the induced subgraph of these vertices is not a kite. The induced subgraph of these vertices considers all edges among all vertices in this in the return. So the induced subgraph of these vertices is actually this weird looking thing with an extra edge. However, because I'm giving you a subgraph, not a set of vertices, the subgraph itself includes all the edges needed to create this kite. It will not include this edge, and therefore I have a kite in this graph. Okay, that's the difference between if I give you back a subgraph or if I give you back a set of vertices that you have to induce the subgraph from. Okay.
Okay, so sorry, I was struggling with the concept of induced graph. So the main difference between the kite and the spider verse is a subgraph and a set of vertices.
Yeah. So a subgraph includes edges, includes vertices and edges. A set of vertices such that the induced subgraph is a set of vertices only, and then you have to go back to the original graph, grab all the edges that are part of that part of those vertices, and that's the induced subgraph.
Oh, so the induced graph only include vertex. It does not include edges.
Correct.
Okay, thank you. That helped.
Okay. Okay, so then let's go over my solution. I have written and rewritten this NP proof so many times because there's I tend to make some mistakes. Let's see if I finally got it right this time. All right. Given an input, check if a solution exists. Given a input graph G and this G to verify, and the solution S, we can verify that the size of S is equal to 2G. Okay? This is one of those cases where we actually have to check for equality because in general, you can sometimes problems are greater than equal to goal or whatever, but in the kite problem, it actually says specifically you're looking for 2G vertices. Okay. We need to verify that the G vertices create a clique by finding all vertices greater or equal to G minus 1. This is how I'm going to isolate my vertices to check. I don't say equal to G minus 1. I have to say greater than equal to G minus 1 because the point at which the clique is attached to the tail. Like this is G minus 1, right? This is 3. This is 3. But this right here is 4. This is not G minus 1. There's 4, right? There's one extra edge there. So that's why you have to check for G greater than equal to G minus 1 and not equal to G minus 1. Okay, and that they have an edge to each other. That G vertices create a tail by taking the remaining vertices and verifying that there is a path joining them to a vertex of the clique. Okay, so I confirmed that I have all these vertices that are greater than or equal to G minus 1 degrees, verify that they form a clique, and then the rest form a tail. Okay. It takes O of n to count the size of S. This takes O of n plus m time to count edges, and each vertex, O of n squared to check for the clique, O of n plus m to check for the tail, and make sure it is connected to the clique, and then overall the runtime is O of n squared in this polynomial.
How can you make sure that there's no additional edge in the remaining G vertices, the tail vertices?
It's a good question. Let's see. I don't think the problem statement forbids it. So if n vertices that form a clique, which I have verified, and the remaining n vertices are connected in a tail, I have verified that. Joined to one of the vertices in the clique, I have verified that. It does not say. Okay, so I drew out this edge, but it does not say that this edge is not allowed to exist, and therefore I don't verify it. I think the implication is that it shouldn't exist, but because when I work on my NP proofs, I just go down each requirement and verify each one. I don't additionally verify requirements that I don't see. So because I don't think I've ever seen that as an actual requirement, I didn't actually verify it. Does that make sense?
Yeah. So this is also a kite.
I think so. I think like from like the technical thing that it is a kite. Maybe. At the very least, if you see a question like this and it's not listed as a requirement, we won't hold you to it, right? Like we can't really say like how did you not verify that there was no other edges between the clique to the middle of the tail, and you come back and say because it didn't ask for that in the problem, then that's that. Like if we didn't put it as a requirement in the problem statement, it's not a requirement you have to verify. All you're doing on your NP proof is to verify each of the requirement you see in the problem statement. Okay? Sound fair? Hope that's fair. Cool. All right. How come when I do this, these circles stuck with it and is grouped, but earlier when I did it, it just started moving all over the place?
Microsoft.
Mysteries of how these things work. I don't know. All right. So if you saw the office hour solution to Spider-Verse, this should not be all that different for you. So what we're going to do is we're going to take the input to click. And again, like I said, start with click, right? Like some people start with like independent set, vertex covered. Like why? Why would you do that to yourself? It clearly says that you want to attach a tail to a click. Why don't you just start with click? And so we are going to create a G prime such that we add a unique tail of G vertices to every vertex of V. Okay, we're going to create this tail so that every single vertex has a tail attached to it. We use G prime and I restate G, you can't just assume G is passed in with you. You have to state it as our input to kite. This takes all of n squared, which is polynomial. It's all of n squared because you're creating all of n tails, and you're attaching it to n vertices, so it's all of n squared. Okay. Again, return no. The kite algorithm returns no. Given the solution S to kite, remove all vertices that have less than G minus 1 neighbors, and return the rest as a clique. I put this extra in that one would think that removing all V that's not in the original graph would be enough, but kite may return a solution that includes a tail that already existed in G. This takes all n plus m time and is polynomial. And the correctness is if a clique exists in G, then we have added a G-sized tail to all vertices to create the tail needed to form a kite with the clique. If there's no clique in G, then since our added tails can't create the clique that's needed, there's no clique to form a solution to kite. This proves that kite is NP complete. And so this is if A has a solution, B has a solution. If A does not have a solution, B does not have a solution. Right. Any questions?
Yes, in the output transformation, how do you, so you say we remove all the G minus less than G minus 1 neighbors.
So I'm trying to remove the tails.
Okay, it's because they might have a degree greater than 1 but less than G minus 1. Because if you say you just remove vertices with degree equals to 1, it's not enough.
Some vertices are degree equal to 2 in the tail
yeah,
part.
The middle of the tail will have degrees of 2.
Okay, yeah, I see. So n plus m is the runtime for finding the degree, right? And for removing the vertex is big O n.
Yeah. Yeah, I just put it all in there together because when you're checking degrees, you can remove start. Yeah, you can just remove them as you find them. You don't have to like do one and then the other. So because I put it into one step, I only give one runtime.
Is this enough? Because in the exam, if we say it like this, if we just give the final runtime without explicitly saying that it takes big O n to remove a vertex, is this going to be enough information? Just saying big O n plus m.
So I will say this: you should write as much as you can, and then generally when we grade runtimes for this topic, there are certain parameters that we are looking for that is not as strict as when we are doing runtimes for other topics. The main thing here is that I am just stating this as a matter of one single step. I say that you're just going to remove all vertices that are less than the degree. I did not say count the degrees, which is one step. Remove all vertices that's of a certain degree, which is a second step. That I would generally put 2 runtimes for. But as you're counting, right, like when you have vertex A, and you count the degrees. At the end of that, you're just going to keep or remove that vertex, and then you move on. I don't need to do it, count all the degrees once, and then come back and remove them a second time.
Okay.
Okay. Any other questions? Cool. All right. Next problem, dominating set. Okay, these next 2 problems, pretty difficult. Oh my gosh, I wrote so much. Okay, I'm gonna go over them, but I will say that both dominating set and feedback arc set is almost. I mean, not almost. It's too difficult to be on the exam. Both of these problems took me like a long time to like write up and several tries. So I would not expect these to be at exam level. So there you go. All right, dominating set. In a undirected graph, we say that D is subset V is a dominating set if every single vertex in V is either in D or adjacent to at least one member of D. In the dominating set problem, the input is a graph in a budget B, and the aim is to find a dominating set in graph of size B. Okay. This is what Wikipedia has for dominating set, and I think it's a pretty good illustration. So the idea is that it's a little bit different. Like you would think, oh, isn't this just, oh, why is this not reloading? Better. Isn't this just a vertex cover? And it's not. It's a little bit more wide-ranging than a vertex cover. So if we look at this, we can see that every vertex is adjacent to one of the red vertices. It's either, excuse me, in the dominating set, or it's a neighbor to something in the dominating set. So if those are our dominating sets, then this is a neighbor to both this one and this one. This is a neighbor to this one, and this is a neighbor to both this one and this one. And then the same thing can be seen in the other two pictures. And you might be asking, well, how is this different than a vertex cover? Well, in a vertex cover, this edge is not covered, right? This is a valid dominating set, but not all the edges are covered, okay? And then this edge is also not covered, okay? So a dominating set takes less vertices than a vertex cover. So that is what a dominating set is. And so now we want to show that the dominating set is in fact NP complete. And if you kind of saw my explanation there, you should, I guess, kind of understand that we're going to go from vertex cover because it's very similar, but not quite. And so how do we turn a vertex cover problem into a dominating set problem? So first, the NP put. So given input, we look for a solution. Given a input G and B to dominate set and solution S, we can verify that the size of S is less than or equal to B, right? That is a easy several points there. And then we can check that every vertex in V is either in D or is connected to a vertex in D. Okay. And so it takes all of n to check the size of S, since S cannot be larger than n. And it takes all of n squared to check if each vertex in V is in D or adjacent to a U in D using an adjacency matrix. So overall runtime is all of n squared, which is polynomial. Okay. That should be the easiest part of this all. And then we'll get into input, output, and correctness. All right. All right. So if we take a input to vertex cover, we create a G prime such that we add an M to each edge, such that we create a triangle with each UV with UM and MV. That is, we add a new midpoint to each existing edge in G and form a triangle. Also, since isolated vertices in G are not part of the vertex cover, we'll be selected in dominating set. We remove all isolated vertices from G prime. So this is tricky. Okay, remember how I said you cannot limit the input from your to your problem A, but you can specially handle some inputs ahead of time in your pre-processing and then do something again with it in the post processing. Okay. And the reason why this matters, and it's really tricky, is that if I had a graph like this, in an isolated vertex up here, the definition of vertex cover would select one of these vertices, or this vertex, right? It covers this edge, and it would select this, and it covers this edge and this edge. But it won't select this vertex. This vertex does not need to be selected to cover an edge. There's no edge to that vertex, and therefore in the vertex cover solution, that vertex is completely ignored. However, if we were to do a dominating set, our solution is now this vertex, right? And then that takes care of this one and this one as their neighbors. It doesn't take care of this one, so I have to select this as my part of my dominating set. But because this vertex right here is not connected to any vertex in my already dominating set, this vertex is actually also part of the dominating set. And that is to say, any disconnected vertex in a graph is always part of a dominating set. But it's also never part of a vertex cover. And so we can handle that by saying, ignore all the independent vertices, and then we'll just add it back in at the end because they're handled that way. Okay. All right. We remove all isolated vertices from G. We set B equals K. This takes all of n plus m to perform on each edge and is polynomial. Output, return no if the dominating set algorithm returns no. Given the solution dominating set, we look at all vertices in D and add it to our vertex cover solution if it is in the original vertex in V. Or if it is newly added midpoint M, we pick either of the adjacent vertices, which must be an original V in V. This takes all of n, since D cannot be larger than n, and it takes constant time to check if U is part of D and and V is part of V, or picking one of the two adjacent vertices. Okay. So we've removed all of these vertices, and we're just going to ignore them because they're not going to be in the vertex cover. And that is how we set up our solution. So what this is saying then is, let's take one of the graphs. Okay. Let me post the correctness and then answer questions. All right. So by creating a triangle for each edge with added vertex M, we make it so the dominating set will either pick U, V, or M to guarantee that every V in our graph is part of the dominating set or adjacent to it. Suppose U is picked, and then UV is covered in G. Suppose V is picked, then UV is again covered in G. Now suppose M is picked instead. Well, in the output, we would just pick one of M's neighbors, which is U or V, which is, as we've said, will cover UV in G. Also, since an isolated vertex in G would not be part of the vertex cover, but would be picked as dominating set. So this is what I was explaining. We can just ignore it. So so this tells us how we get the if there's a solution to dominating. So this tells us if there's a solution to dominating set, then there's a solution to vertex cover. If no solution can be found for a dominating set, then UV and M were not picked for some triangle, and since UV and UV were both not picked, we know that UV in the vertex cover problem was not covered, and so no solution was found for vertex cover. So this is arguing the if B has a solution, A has a solution. If B has no solution, A has no solution. I'm not sure why I chose this direction on this one. I normally don't do it this way. I must just have been feeling kind of feisty on this one, but that's the way I did it. All right. Any questions on this problem? Oh, I got hands. Yep.
Yeah. Sorry, I may have misheard or misunderstood, but earlier, did you say we can't limit the input to the problem A, so the problem that we're reducing to?
Yeah, you cannot specify which of the inputs to A you are going to deal with. Like I can't say, okay, so you know how I said like, okay, well, my dominating set doesn't work well when I'm trying to work with isolated vertices.
Yes.
So I cannot say that my problem A is going to be vertex cover such that I have no isolated vertices. That's not allowed. You can't arbitrarily limit which inputs that your vertex cover would solve for, because vertex cover has all these other inputs. What I can say is that given a input to vertex cover, if it has isolated vertices, I am going to do this to it before I send my transformation to dominating set.
Okay. I mean, I guess I'm having a hard time understanding if you didn't do any transformation to the input in this case, and you just sent it. Sorry, if you didn't remove the vertices, the isolated vertices in this case, but you did add the new midpoint ones, and you sent that in as input, why would that not work?
Because eventually in the dominant set, you are going to pick those isolated points, but you have a very limited budget for it. And maybe it will tell you that there's no solution. But in fact, if you don't care about those isolated points, you only care about the non-isolated point, you may still find a solution.
Okay.
Right.
Yeah, because the budget is what actually causes an issue. I see.
Yeah, so the green here is a vertex cover. But my minimal dominating set is actually those two plus this one. And that's going to mess with my budgeting constraints or what I do. I mean, I guess the other way you can count the number of isolated vertices and add it to your budget, and then your dominating set will select all the isolated vertices and whatever is needed for the rest of the graph, return that to you, and then the output transformation, you go for all isolated vertices, remove it from my solution, and return the rest of my as my vertex cover. But that seemed a lot more convoluted than just ignoring them to begin with. I think that would work. Okay. Any other questions? All right. We are going to move on to. I'm actually surprised there's no question. It's like most people don't like allow me to just do this and move on. All right, last problem. Feedback arc set. This one's a toughie.
I think it's easier than the previous one.
It can be. I think it depends. So I think the feedback arc set is actually a very difficult problem, but at the same time, you're given a lot of clues based on the problem statement, so you can kind of use those clues to your advantage. But like if you were just handed a feedback arc set, problem, I would find it rather difficult. All right. In task scheduling, it is common to use a graph representation with a node for each task and a directed edge from task I to task J if I is a precondition for J. This directed graph depicts the precedence constraints in the scheduling problem. Clearly, a schedule is possible if and only if the graph is acyclic. If it isn't, we'd like to identify the smallest number of constraints that must be dropped so as to make it acyclic. Given the directed graph, a subset is called a feedback arc set if the removal of edges renders G acyclic. Feedback arc set. Given a directed graph and a budget, find a feedback arc set of less than equal to B edges if one exists. Show that FAS is in NP. FAS can be shown to be NP complete by reduction from vertex hover, so that's a hint. Given an instance of vertex hover where G is an undirected graph, we want vertex hover of size less than equal to B, blah, blah, blah. If G, then make K. All right. Hold on. What is this?
It almost reads like B and C are saying that they want you to do the vertex cover transform and then like explain the input and output transforms.
Yeah. So I'm just gonna. So basically, all of this, I'm just gonna write it as a NP complete proof. But I will say that this is where I got the influence from. So NP proof is part A. Let's go there. Given input, we look for solution. So we have this input to our FAS and the solution S that we can verify. I got locked out. We verified that our size of S is less than or equal to B. Always do that. Oops. Okay, so that's one of your verification steps. Then we can create a new graph such that we remove the feedback edge set so that we get this thing and check if G is acyclic by or DFS by and checking for packages. Yep. I think the other thing you can do if you wanted to is to run SCC on G, and then the size of SCC is equal to size of G. Because if there's the same number of SCCs, it means that nothing was created a cycle, and so this also works, and so that's also open pleasant. Okay. If it takes O of M to check the size, O of N plus M to construct G, and finally O of N plus M to run DFS over run times O of N plus M is polynomial. So this is our NP proof. Any questions on that? The given, the input transformation is given to us kind of weirdly. So it says that given the directed graph G equals V, a subset, FAS can be shown to be NP complete by reduction from vertex hover, given an instance of vertex hover with G's on a graph. So we basically do that. So basically for every edge that is in our vertex hover problem, we create a cycle between UV and new vertices U prime, V prime. Thus, an edge in G is a cycle in G prime. So basically what we are saying is that UV, create a cycle between UV and UV. So if we had a vertex, a edge in our original graph, what are we going to do? We are going to n vertices, and then we make G direct graph with 2 n vertices, okay? And n plus 2, okay? For all 1 through n. Yep. And for every v, I, v, j. So this is u, this is v. Then we want to make a secondary u and a secondary v. And we say that for every I, so that to j. So if u is going to v, hold up. Why did they use I and j and then prime? That's so confusing. So if u and v has a edge, then what?
If I'm understanding it right, I think you want an edge from U to U prime, yeah.
And then from, I think we do this to that.
I think you want U prime to V and then V prime to U, so it's like an X.
Like that?
I think so. Yeah, from the prime to the not prime of the other vertex, yep.
Okay.
I think your U prime and V edge needs to be reversed from U prime to V. Instead of you have it V to U prime right now.
Like that? Okay. Okay. It's so confusing. I hate this problem. Okay. Let's continue on and see if that makes sense. If not, I'll make adjustments. Okay, so part C is asking for the output, I think, right? Okay, C, show that if G prime contains a feedback arc set of size B, then G contains a vertex cover of size at most B. And given the feedback set, arc set of size B in G prime, you may need to first modify it slightly to obtain another one, which is a more convenient form, but is of the same size or smaller. Then argue that G must contain a vertex cover is the same size as the modified feedback arc set. Okay. Right. So we turned out, so for each feedback edge in FAS, one of the endpoints must be the original vertex in G. Add that original endpoint to the vertex cover. So if the edge is between WI and WI prime, then add WI to the vertex cover. If the edge is between WI prime and WJ, then we add WJ to the vertex cover. If the edge is between WI and WJ prime, then we add WI to the vertex cover. This takes O of B, but since B is less than or equal to M, the overall runtime is O of M, which is polynomial. Yep. I think I remember what I did here. So we created this. So for every UV in edge, we create a cycle between UV and U vertices UV. So UV. So this creates a cycle, and then this also creates a cycle. But I think I also need I think this also has to be created, right? So basically what I'm saying is that I have these cycles here where U goes to U1, U prime goes to V, goes back to U, or I go U to V to V1 to U. Now, in order to remove my, in this isolated two vertices, I'm doing a vertex cover. So I only want to pick one of these vertices. In order to remove the edges here such that I don't have a cycle, I would either remove this edge, which gets rid of my cycle, or I would get rid of this edge, which gets rid of my cycle. And if I remove U prime to V, then V is the original vertex that I add to my my vertex cover, and that covers these two vertices. If I was to instead remove this edge, then I would put U into my vertex cover, and that covers that cycle and that edge. So it just kind of makes the equivalent of making every single edge into a cycle upon itself, such that when you go and remove the cycle, it tells us one of the vertices that we need for that vertex cover. Okay. And then I go into more detail on the correctness. And so again, this was given, kind of given to you by the problem statement. Otherwise, not sure I would have been able to figure out that solution. I'm going to go out on a limb and say I definitely would not have been able to figure out a solution. And so then our correctness is that for every edge in G, we create a cycle in G prime. We do this by creating directed edges between vertexes Wi and a new vertex Wi prime. We then create an additional edge between the two already connected vertices such that it goes in the opposite direction of the original edge. Thus, a cycle is formed. Each cycle represents exactly one edge in G. So for the cycle to be removed by FAS, an edge which involves an original vertex must be part of the FAS. It is a one-to-one relationship. Removing a cycle in G prime exactly covers one edge in G. If IS cannot find a solution for G prime, then because each cycle represents one edge in the original G, we also cannot find a solution for vertex cover in G. So this one is if B has a solution, then A has a solution. And then if B has no solution, then A has no solution. And that is the feedback arc set. Any questions on this problem?
None come to me now, but I'm sure as I'm reviewing it, I'll have plenty.
That's fine. All right. That concludes our set of problems.
Thank you.
We're going to be done in under 4.5 hours. All right. So let's go to discussions to see if we have any more questions. Hopefully I answer most of them. Let's go to sort by oldest. All right. Hope this is a shorter study session. Sure is. Here's all the problems that's being asked. Answered. Will you still be doing an overview of LP? I kind of did that. And then same student recommended Emily's guide, which I definitely think you should do. Go over allocation problem, homework 8. So that ended up just being the set cover problem. I mean, set cover and the allocation problem, I think, is basically a one-to-one. So if you had like, kind of studied up on set cover, you could have just like, it's one of those like equivalency problems, right? Like it's basically a set cover and you could have just argued the equivalency and then you'd be pretty much set. If not, I did go over the vertex cover to set cover problem, and that is exactly how you would go from vertex cover to the allocation problem. Can you please solve 8.10e sparse subgraph? Yeah, let's do that. I feel bad because I took a vote and then this person asked very specifically for one problem and I didn't see it. Let's see, 8.10e. Sparse subgraph. Ask, given a graph of two integers a and b, find a set of vertices G such that there is at most b edges between them. This is very similar actually to the what was the problem with the ingredients matrix kind of problem that we went over?
Experimental cuisine.
Dish, yeah, 8.16. It's very similar in that we want to forcefully make it so that we select nothing. Well, we select things that have nothing shared. So we verify it by checking that the size of S is equal to A, and edges between X and Y in this solution add up to less than or equal to B. That's our budget. Now input, we're going to get the independent set, and we're going to say we're going to set A to K. So K is find this many vertices with 0 edges between them, right? So that's exactly what independent set is. Find this many vertices with no edges between them. Pass this in, and then we return exactly as is. And so we use space subgraph to find independent set of size K by looking for A equals K vertices that share 0 edges between them. Independent set has exactly 0 edges by definition. So that is how we do sparse subgraph. Okay, go back. Understand you won't cover any specific linear programming problems, but can you at least cover high-level tips? Learn the math, remember the rules, remember the different definitions, remember how to convert from dual to primal, primal to dual, remember objective functions, constraints. Yeah, basically remember all the words and the math between them. That is how a math problem happens. Yeah, there's nothing like really specific I can give you. There's no like super secret sauce. One of the yeah, I don't think there's much you can do other than practice and try to memorize the different parts of it. Oh yeah, the weak and strong duality, and then the yeah. Okay. Go over homework 7 and homework 8. So homework 7 is the Spider-Verse, which is very similar to the kite problem, which I did solve. I also mentioned what I think the spider problem should have been. And then homework 8 is very much the set cover problem, just disguised. And so I did give a solution for the set cover problem. So that should cover you. And if not, then I think Dr. Priddle's office hours should be good. So remember how I told you that we can't have nice things because people unfortunately break rules? One of the things I'm actually going to stop doing starting from this office hours and next semester is that I am not going to present written solutions to homework problems. Yeah, unfortunately, some student took my office hour solution from last semester and turned it in as their own. And technically, it is a it is class material. So technically, like, no rules are being broken, but it certainly hurts the, if not breaking the law, it definitely breaks the spirit, I think, presenting my solution as your own for your homework. So I talked with the other TAs about it, and one of the things that we're going to do to sort of curb that is to, and I think Rocco was doing this. If you've taken other semesters, when Rocco goes over his homework solutions, he goes over a very high level view instead of writing it out. And I think that might be the direction we go from there. Sorry. Let's see. Following questions. MP complete problems with budget B or target G. Can we both use both forms, less than equal to B, n equal to B, greater equal to G? And I said that. So a lot of these MP complete problems, your known problems, they have very different like versions of it. Some of them is exactly G, some of them is less than equal to G. I think it's okay to use whichever fits your purpose best. Okay. 8.19, the treatment of almost trivial cases G is less than equal to 3 is tedious. Can we ignore them and assume G greater than 3? Yes. So there's two things. One, we tend to be pretty lenient on that, is that we do understand that we don't want you to have to like focus almost all of your time on this tedious case and then not enough time on the very general case. One thing you can do is say, within reason, don't go like, go overboard, is that, assuming that G is greater than 3, here is what that solution will be. And I think that should be good. So yes, you can do that. 8.20, I plan to show that VC reduces dominating set. Before that, can we assume that G does not contain any isolated vertex? The vertex are not connected by any edge. Otherwise, it's hard to show that a VC solution is also a DS solution. Good job on the thought. And no, you cannot do that. You cannot assume that your VC input does not have isolated vertices. But for the solution that I provided, I showed you what you can do about that. You handle those isolated vertices and you just ignore them. You cannot say that my input to vertex cover specifically doesn't have isolated vertices. But in your transformation of your vertex cover, you can say I am going to explicitly ignore these isolated vertices. And you should explain why in your correctness, why you can do that, right? You should always give a reason why going from one input to the other through your transformation is equivalent or okay to do. You can't just do it and then just like not say anything about it. Next, can you go over 8.8? Input transformation solution says, what's 8.8? Is this one of your practice problems, 8.8?
It looks like 8.8 is 3 set to exact 4 set. Or sorry, exact 4 set.
Yeah.
And that was okay, and that was released as a practice solution?
Yeah.
All right, so let's explain specifically why there are at most n+3 variables. If each single literal forms a clause, and don't we need at least 3 n variables? Can we use the same set of variables for each clause? I'm going to try to read the solution. I don't actually know what this provided solution looks like. I will try to read that and answer these questions. And hi, Joves, would you mind going over H7? So I explained what induced subgraph is, but I can kind of, and I use that as like basically my example for all the graph ones, right? I drew the click, I drew the legs, and I said, you have to add attaching the leg to everything, and here's why. And I said, with an induced subgraph, what's the difference between an induced set of vertices to induce a subgraph from, and the different and what a subgraph provided to you from kite is. And I also explained why you have to remove the legs that have a certain degree rather than just removing all the vertices you added. And I also explain why that takes O of n and not O of n squared. So I think like if not in one place, I covered Spider-Verse pretty extensively on throughout the day.
Yes, thank you.
Yep. Right. And so general exam tips, they're always going to be the same. You should rest before the exam, get yourself in a good mental, emotional state, try to be relaxed, try to slow down, try to read the problem, read it again and again. It is extremely important in NP complete problems to read the problem correctly. If you read it incorrectly, you're going to have a really, really tough time getting the right reduction. Knowing what the requirements are and the restrictions are super important. You need to know what the requirements are so you can verify them in your NP proof, and you need to know what the restrictions are so you don't make a bad transformation. I've seen lots of students who just gloss over the requirements of what the unknown problem is, and then they create a input transformation that breaks those rules. If you break the rules of the input transformation, one, it's going to be either way harder or way easier than they should be. We tune these problems to a certain difficulty, and so if you misread the restrictions and you don't properly restrict your scope, they could be way harder than they're supposed to be. If you don't read the restrictions and you use a input or a number that you're not allowed to use, it can make the problem also way easier. And either way, you're gonna either lose a lot of points because you solved the wrong problem, or you're going to lose a lot of points for breaking the restrictions. So make sure you read the problem correctly. Write them down, jot them down as requirements, jot them down as your restrictions. Okay. Write down your multiple choice question answers. Again, you're going to go into the following week, and people are going to discuss which answers they got on the multiple choice questions. If you're trying to avoid that completely, that's fine. I know that some students are like get really anxious seeing what other people think the solutions are. I know for myself, I would be super anxious not knowing what those solutions would be. So I always write them down to compare with other students. Again, don't select the right multiple choice questions, eliminate the wrong ones. And I like to answer the multiple choice questions first. If you've been in my office hours before, you'll know that I like that so that I know very, very much how much time I have left for my writtens. If I start the written first, I may not have enough time to go through all the multiple choice questions, and then I panic. If I do the multiple choice questions first, then I know that I have, an hour and a half left as I'm writing the solutions, and as I'm running low on time, I can be like, okay, I'm going to be a little bit less detailed on this just so I can get through it, because I get partial credit if I don't get everything wrong. I might get full credit, and that might be what's required. But if you don't get to the multiple choice questions in time, it's always just going to be a 0 because you never answer them. So that's the danger of that. But do whatever works from you, and then enjoy the exam. So this is possibly for many of you the final exam you will ever take in an academic setting, right? Like if this is your final class on your final degree and this is the final exam on that, you may never take an exam again, not in the type of setting that you have now. So take it seriously, but try to enjoy it. It's always like kind of one of those things was like, yeah, I might not ever experience this again. So try to have fun. I think that's it. Does anybody have any other questions before we end the office hours for the day?
Thank you.
You're welcome. It's been my pleasure working with all of you. So, if I don't talk to you again, if I don't see you again, good luck with, the rest of this semester, the rest of whatever time you have on in this program, and the rest of what you plan to do after you graduate. And Asia will always say, "Go spend some time with your family." So I will echo that those advice. Go spend time with your family afterwards.
And for you to spend time with your family too. Thank you. We appreciate
yeah.
it.
No problem. All right. Good night, everybody.
Thank you for everything, Joves. In the best way possible. Hopefully, I don't have to see you next semester.
Yeah.
Hopefully, we don't have to see any of you again in this program.
That's true.
Respectfully.
Respectfully. Yes.
If you're like some of the alums that really enjoy chatting with us, you can always stay around in the public Slack that we have. And you know, some of the if
Do
you
you
ever
have a
noticed some
link
of the
to that?
alums. What's that?
I've heard so much about that Slack channel, but I've not seen a link to it, and I rarely use Slack.
Ask in the office hour thread. I'm sure someone will provide it. It's pretty active. And then from each semester, you can see the other students go through the same panics you did, and you'd be like, oh, I went through that. Isn't that cute? And then you can give them words of advice and words of encouragement.